Welcome to this video. We're going to start going through the PyMC documentation. So let's just jump right in because this is going to explain all of the relevant context that we need for what this is and eventually what we want to use it for. So PyMC is a probabilistic programming library for Python that allows users to build Bayesian models with a simple Python API and fit them using the state-of-the-art algorithms such as MCMC or Markov chain Monte Carlo methods and variational inference. Now let's talk about the features. The features, at least in the very broad strokes, I wouldn't say that they're actually talking about this in a strict software sense of, software features, but related, tangential, broad strokes, features. PyMC strives to make Bayesian modeling as simple and as painfulless as possible. It can be pretty painful. So for example, if you've looked at Bayesian workflow, that's the archive paper right there. Let's take a look at the PDF. You can go through, a 77-page long abstract paper of preprint paper on Bayesian workflow, and there's this lovely diagram that they have that describes the kind of workflow that you might go through, and a lot of these are addressing problems that come up in the modeling process. So it can actually get pretty complicated, and it's quite iterative. You have to come back to earlier steps with refinements, and then check, and then refine, and then check in various different ways. So it's going to make some of those steps a bit easier for iterating. And it also allows the users to focus on their problem rather than on the methods. Now, sometimes that's good. I would say that sometimes that's also not good. Sometimes being forced to really think about what you're working on more deeply can help expose flaws that you would otherwise not detect if a tool was making things, in some sense, too easy enough that you're not thinking about what you're doing. You should think about what you're doing when you're doing Bayesian inference. So anyway, I don't think that's a problem for using PyMC per se, but it does come with trade-offs at the end of the day. So here is what sets PyMC apart. So one thing is that it's modern. It includes state-of-the-art inference algorithms, including MCMC, which we mentioned before. That's the Monte Carlo Markov chain approach, as well as specializations of it, in some sense refinements of it, like Hamiltonian Monte Carlo, as well as here we have NUTS, which is the no U-turn sampler, which was published in, I think, 2014 by Gelman and someone else. That is a kind of algorithm for making MCMC more efficient, as well as variational inference, which is a kind of approximate approach, and there you can use auto-diff variational inference, ADVI. Okay, and the other thing is that PyMC is supposed to be user-friendly. So you write your models using some kind of Python syntax, which for some people is going to be easier. And learning Bayesian models is one of the things that you can look at in their documentation. You can learn it by example from their notebooks. So that's also pretty good. We might do some of that ourselves, but I'm here partly to do a kind of, I don't want to say comprehensive because I don't know if I'll cover everything in the documentation here, but going through the broad strokes and making sure I've gone through all of the getting started material and then beyond. So the other thing is that PyMC is fast. It uses PyTensor, which is a kind of auto-diff and numerical kind of library that does compilation for you into C. You can also use some other kinds of backends that involve like Numba or JAX if you're familiar with those. And you can run your model on your GPU and benefit from so-called complex graph optimizations. Some of that may be at the level of the sampler. Some of that's also just cool algorithms that PyMC uses behind the scenes for adjusting models. You can turn one model into another model, which is kind of great. So model transformations, not just data transformations. And it's, so-called batteries included. It includes probability distributions, Gaussian processes, which is one particular type of stochastic process that could be done in a Bayesian way or a non-Bayesian way. Approximate Bayesian computation, which is great for when you don't have an explicit likelihood function. I am struggling to remember. Oh, sequential Monte Carlo. What's SMC? Sequential Monte Carlo methods that also can improve some sampling and much more. Okay. That's great. So it integrates nicely with RViz, which is for visualizations and diagnostics. That's where you can look at some nice forest plots and trace plots of your sampling results. And it's also something that other packages have been built on top of, such as Bambi for high-level interfacing of mixed effect models. There are some cool examples in Bambi. One of my favorites is it has a circular distribution example. I think they use FunMe's, and you can model probability density functions on a circle, which is great. It's also community focused. You can ask questions on Discourse and join meetup events and follow them on Twitter, and you can even contribute, of course, to the library because it is an open source Python package on GitHub, and as far as I know, they have rules about who and how you can add or contribute to the code, but by and large, anybody can do it if they're willing to go through the process. Getting started, there's installation instructions, which we're only going to install this one way that is, I guess, somewhat biased towards how I work on both Windows and Linux, and we might come back to that at some point. There's a beginner's guide if you don't know Bayesian modeling at all. There's the API quick start if you do know Bayesian modeling, but you're not familiar with the basically the API, the application programming interface. There's an example gallery, which I think is one of the more comprehensive and useful pieces of PyMC beyond learning the basic API, is to look at the various ways that you can use it for dealing with missing data problems, doing causal inference, doing sensitivity analysis, doing model comparisons, and so on. The examples are quite useful for that. And then there's the Discourse help forum. Great. So we can finally jump into an example here, I think. So an example from linear regression. Now, if you've done any kind of statistical modeling, you might start to look at something like linear regression and go, what's the point? Of course, you can do linear regression with many different tools. In some sense, linear regression is chosen here not because it makes the strongest case for Bayesian modeling, but because it's just an example that most people with some kind of statistics background is, they're going to kind of understand it. So this example demonstrates how to perform Bayesian inference for a linear regression model to predict plant growth based on environmental factors. Plant growth can be influenced by multiple factors, and understanding these relationships is crucial for optimizing agricultural practices. Okay, so that's not a lot of work on the background information, but the point here is to learn how the interface works, not to become plant scientists or agronomists or whatever is the relevant term here. So independent variables. Independent variables is a tricky one where, in some sense, when we're talking about it in regression language, it actually doesn't necessarily mean that they're statistically independent. It depends on the family of model, and so that also depends on how narrowly are we using the word linear regression. But suffice it to say, we're going to call them independent variables. Sunlight hours, like the number of hours that the plant is exposed to sunlight on a daily basis. The amount of water, so the daily water amount given to the plant in milliliters, and the soil nitrogen content. So that's the percentage of nitrogen content in the soil. Of course, that could come about in different forms of nitrogen, right? So that could be nitrates or nitrite. In some cases could even be ammonium. And how bioavailable and bioaccessible that is just depends on more details that we're not going to, honestly, we're not going to cover in this example. So we have a dependent variable, which is plant growth, which is represented by the small letter y for just ongoing conventions that we have in statistics about how we like to name variables. And this is defined here as measured as the increase in plant height in centimeters over a certain period. So in some sense, if it, I haven't read ahead to the example to know if it's really this, but if it's the change, then it's already something like a finite difference, right? Over a certain period, maybe it's like a fixed period. But if it's an amount of change, then it's not actually the amounts, which is something to keep in mind if you're thinking about this as kind of a dynamical system, that maybe the plant had some initial state and then it grew from that, and maybe the initial state matters, and maybe other things like the boundary and initial conditions matter. Even if you're not strictly speaking using differential equations, that kind of thinking from dynamical systems theory can still be useful for understanding the limitations of a model. This is possibly one of the ones to think about here, as we're just imposing linear regression to model growth. I don't even know if this is real data. It doesn't look like it is. No, it looks like it's fake data, but that's fine. That's not the point of the example, really. So we're going to throw away all of the concern about the science part because, they're basically taking a little shortcut here anyway. Okay, so let's build out our example. I'm just going to go create a directory here, welcome, and we'll just call this linear regression. And it could be tempting at this juncture if you really didn't care. I mean, you just copy it and then, paste the whole example. That's probably fine, but I think I actually want to go through the whole example because I think that there's more value in one typing out code. You get more familiar with interfaces that way by getting that kind of practice, but I think it can also put a little bit of a pause so that you actually think about what's in the code instead of just going, great, copy pasted it, I expect a result. We're not here to do vibe coding in this video. Okay, so import PyMC as PM. Actually, I'm missing something. Let's take a step back here and let's just initialize a project, and we'll go uv add PyMC. Great, so that's done. We have the package. I am just going to yes, okay, let's just go source venv activate this virtual environment. We're all synced up, and now we can start the example. We already wrote out the import statement for the package just to make sure that that's working as I expect. We can run it. There we go. So let's start by creating a synthetic data set, taking draws from a normal distribution. So on a real problem, I mean, you'd be pulling data, right? We'll define a seed number here. We'll call it 42. Douglas Adams reference. Now we're going to start defining some probability distributions using PyMC to actually generate the data. You can use whatever you like, as far as I know. Like you could use, you could use NumPy, for example, at this juncture if you wanted to. And I think some of their examples do. But anyway, we got xdist, and we've defined some kind of shape. And then we can go xData. So the data is the specific instance of those random variables. And we can pass in random seed is equal to our seed. And it's not dists plural, it's just dist. Okay, so we've taken some draws. Maybe we want to take a quick look at what this is. Python 3 linear regression. So it prints out a big array. Sorry if you didn't catch that. Let's just do it in the command line here. Yeah, you get a big table. So these are our samples. You can see there should be 100 rows, and there's 3 columns, which we can at least see the columns easily enough. Presumably there are, in fact, 100 rows. We'll trust it. All right, and then we'll move on to something that we will definitely talk about more with PyMC, which is coordinates. We're not going to get into it now in detail, but suffice to say it allows us to describe something about the structure of the data so that the model can keep track of that structure. So define coordinate values for all dimensions of the data. And again, the word dimension there with PyMC is being used in a kind of special way. So we'll define this dictionary, coords, and we'll give this one a name of trial, range of 100. And we'll say there are some features, predictors, which we talked about as our so-called independent variables, right? So we have sunlight hours, and we have water amount, and we have soil nitrogen. Now we're ready to define a model. We have some data, and we've defined this coordinates thing. And we can now move on to saying how it all goes together into a statistical model or a generative model. And often we like to emphasize this idea of generation with PyMC and Bayesian modeling because that is essentially what it is. It's a sampler, and it generates examples from some candidate probability distribution, supposing that it's well specified. So we're going to use this thing called model. It's a class, encapsulates the variables and likelihood factors of a model. The model class can be used for creating class-based models. That's fine. And to create a class-based model, you should inherit from the PyMC model and not override the dunder init with arbitrary definitions. Do not forget to call base class PyMC model dunder init first, blah, blah, blah. All right, so there's some stuff that can go in here, but we're not going to read the documentation inside of the documentation every time. We're just going to trust that there's this thing called a PyMC model, and we're going to pass some things into it so that we can use it. We have chords. We'll pass in our instance of chords, and we'll alias to call this our generative model, just like they do in the documentation example. And we're in a context manager. Notice the with keyword there. So we'll say x is equal to PM data. We're going to create one of these things called a data container. They're very useful when working with complicated models, but we're not going to talk about it until they talk about it. We have the trail, and we have the features, which we'll pass in as a list. So far, so good. We've basically defined something about the data that goes into it, and then we will say model parameters. Now, I wouldn't say that every model needs to be formatted exactly the same way, but there are some tendencies. Often you do a certain amount of setup with the data first, and then you start defining some parameters, and then you start defining maybe some functions that involve the parameters, and then you get to the bottom, likelihoods of the model. Likelihood or likelihoods, depending on how complicated of a model it is. So we'll go PM normal. We're actually grabbing probability distribution, right? This is a univariate normal distribution, and they talk about normal distributions there. We're not going to get into that right now. We'll leave that alone. Betas. So here there's a tacit idea, betas plural, not just beta, that there's going to be multiple of these, and that's going to correspond to the dimensions of our features, or our features are going to make the dimensions. So there's going to be a beta for each of these: sunlight hours, water amount, and soil nitrogen. There we go. And sigma. Here they're going to say a half normal distribution. It's a whole can of worms on what kind of probability distributions you would choose, but a half normal here is going to be a kind of prior on the amount of spread in the likelihood, so that should be fine. I mean, I don't have any reason with a made-up data set to disagree with that. So sigma, half normal distribution. If you don't know what a half normal distribution is, maybe you can quickly look it up. But it's a kind of like folded distribution where we cut off at 0. Yeah. So half normal density. And so a normal distribution would normally look like this yellow line, but when you basically, through change of variables, include only positive values, you get more density on the positive because there's only the positive and there's 0 density everywhere else, because normalization, it must integrate up to 1 in order for it to be a valid probability distribution. Oh yeah, you could think about this as a change of variables then. So, if x follows a normal ordinary, a normal distribution with a mean of 0 and a variance of sigma squared, then we can define through change of variables that y is equal to the absolute value of x follows a half normal distribution. In other words, it's the distribution you get when you take an absolute value. There can be some weird consequences to that when most of the original normal distributed variable x is mostly over the negatives, like most of the original density. You can get some weird things, but we're going to trust that this model is reasonably designed because it's supposed to get us started. So linear model. Now we're going to define a function on what we've defined here. We're going to take mu and x and the at symbol, which is going to be basically your kind of row against column matrix multiplication kind of operator. So betas here is it's going to say it's a tensor variable. We kind of know that it's going to be a random variable, right? And then this is our data. So we're multiplying those together. Let's define the likelihood of our model, or in other words, the probability or probability density of the data given other stuff. What stuff? Well, given these betas and sigmas, which are, in a Bayesian context, they're random variables. So assuming we measure deviation of each plant from baseline, okay, we'll say that plant growth is going to be bound to the value of, it's going to be normally distributed. I don't think I would actually believe that growth is always normally distributed. Like if you're dealing with very small growth values, like the plant's not going to shrink due to, I mean, I guess it could in a way shrink because of like loss of water or something, but I think a lot of cells in a plant don't get like ungrown, like reabsorbed or something. So anyway, we're not going to try to do plant science here. Let's just stick to PyMC. So we've got plant growth. It's going to have our average mu, which is going to be defined as this. Essentially, it's an inner product, a dot product of sorts. And we're going to have sigma as the amount of dispersion for our normal distribution representing the plant growth. And then we'll have dimensions is equal to trial. So that so far should be sufficient to just define the model. We haven't sampled from it. We haven't in any sense like fit it to data. And assuming there's no typos here, we should be able to also just run it, although it shouldn't tell us really anything all that interesting at this juncture. But that's our model, right? We have that plant growth is normally distributed, and that if we take our x variable data and multiply it by these random betas, and then also accept that there will be some amount of uncertainty in the likelihood due to other unexplained factors, measurement error of some kind, that we get our plant growth variable from that. Notice in this example that we're not treating the x values, the data, as random. That it's not like we're treating x as a random variable or a collection of random variables. We're just saying with these instances, you multiply it with the random vector and then pass that along into the plant growth, and that we get random plant growth from whatever a fixed value of x is. Does that make sense? They're not random variables in this model, but in some models, that's exactly what you could do and maybe in some cases would want to do. Okay, so that's our model. Let's talk about generating data from the model by fixing parameters. So you can sample from a model with fixed parameters. In some sense, it gets kind of weird. We're talking about, like in Bayesian inference, we're talking about a probability distribution that has parameters, but the parameters are random. So you think about it maybe first as like sampling those random parameters, and that gives you at each instance of the random parameters a probability distribution. And so it's a kind of, in this case, it's an infinite mixture model is one way to look at it. But anyway, let's not get too far down the math path. We'll just say that we're going to have fixed parameters, and that we're saying normally, typically in PyMC, these are not fixed things, but PyMC allows us to fix them to specific values if we want. So here are sigmas and betas. Only sigma here is just going to be 0.5, but we have our 3 different betas corresponding to sunlight hours is going to be 5, water amount is going to be 20, and soil nitrogen is going to be 2. Great. So now we're going to use this do operator, which was actually just introduced a few years ago. I mean, PyMC is one of the packages that has kind of acknowledged the importance of modifying models to answer kind of counterfactual questions. And in some sense, that's what this is to look at one of the most common types of things that we do in causal inference, at least from a Judea-Pearl framework, is we will mutate the model or change the model, make a counterfactual or hypothetical adjustment. So we're going to say with PM do, and do is going to operate on our generative model. Fixed parameters, expected indentation block. Yeah, but there's also an issue here with fixed parameters. That is the correct spelling. Doesn't like something about it. There's a type issue. Well, we'll see if that actually causes a problem. But we're going to take some inference data. So we're going to go inference data or I data. as a shorthand convention in how people name it. You don't have to call it iData. You could call it something else. But we're going to say random seed is equal to our seed from the top. And that gives us, oh, I'm jumping lines here. My mistake. My goodness. Okay, so we're doing this do operator thing. We've got our fixed parameters. We've got our accidentally clicking on the interface to get API documentation. Okay, no, what we want to do is sample from this model. So let's go inference data, PM, sample, prior predictive. That is the sampling from the distribution, basically without having used Bayes' rule, without updating the parameters with respect to the data. So now we'll pass in random seed is equal to our seed number, and then we'll say synthetic y, which is arguably a form of synthetic data, idata.prior. I'm going to put plant growth in there. And cell, I believe, is select. Doesn't tell us that, but I think that's what it is, and that has to do with the kind of data management tool that's behind the scenes. And we'll be selecting draw of 0 and chain of 0. So there's the number of draws within a chain, and then there's the number of chains, which is, if I remember right, it's usually 4 by default with PyMC. So chains are basically the number of sequences of samplings that you got, and the draw is the sample, if I remember that correctly. All right, so let's run that. I mean, that's going to take a moment, but I feel like it's worth running these different pieces, make sure that we don't have an error due to typos or whatever. So it did the sampling, but it hasn't shown us anything because we haven't like visualized anything yet, but the code's apparently working. So we just took, what did we do here? We defined this model. We said, well, what if we actually fixed some of the parameters to specific values, and then we created a model. So this is a kind of model transformation where we're not stuck with a completely rigid set of assumptions about what the model structure is. We can change the model in some ways, which is nice. And then we did a sampling from the model, from the prior predictive distribution. So did I say prior before? Hopefully not. This is the prior predictive. So you can sample from the prior, but then you can look at what's the probability of new data given old data. And that's where we got this synthetic Y from. All right. Then we're going to do some inference, some Bayesian inference, one might even say. Infer parameters conditioned on observed data. All right, and I think we're probably, looks like yes, we're going to basically ignore this synthetic model. We're not reusing that. We're still basing it off of our original generative model. So here we're going to go PyMC or PM observe, and we're going to pass in generative model. That's what we defined up there. And we're going to pass in our, not fixed parameters, we're going to pass in plant growth. Oh, you know what? I tell a lie. We did get some synthetic data. Look at that. What a clever example. It actually makes sense. Synthetic Y. Okay, we're going to grab our synthetically sampled values, and we're going to call this model inference model. Now, if you're working with real data, you're not going to do something to create synthetic data usually, because you're usually going to be interested in some real data. I'm not saying that synthetic data based purely on models is never useful. Like, you might do an analysis that's mostly just based on assumptions and go, suppose the world works this way, what is the result going to look like? That kind of simulation can be useful, but often in Bayesian inference, we're interested in making inferences based on some real data, because we usually are not comfortable with, or shouldn't be comfortable with, just assuming that we know how the world works without some kind of external information from the world to tell us how it works. Data can help with that. So we're going to do a sample. Notice that this is just called sample and not sample prior predictive. These are different distributions. So generate samples from the prior predictive distribution as opposed to draw samples from the posterior distribution using the given methods. So this is actually sampling parameter values, essentially. So PM, what was the last thing? Oh, we're going to look at stats. Summary pass in our inference data. Where are we getting the inference data? We're getting it from right here. Inference data, and we're going to select some variables because we're not going to plot like every piece of the model. We're going to grab the betas, and we're going to grab sigma. So that already should be enough to actually calculate the statistics. And just for some notion here of completeness of the example, we'll do a print statement so that we can actually have a table to look at, right? Obviously, you might want to do something more substantial when you're trying to productionalize a PyMC model, but you know what? This print statement should be fine. Let's run the model. So this is going to take a little bit longer, or you're just going to get compiler errors because I need to install, I believe, it's missing the Python header file. So let's grab Python dev. Okay, we're running it again because we needed a compiler and we were missing a compiler. So now we have a compiler and it's generated our synthetic data here, and now it's doing an analysis based on, okay, well, I see this is actually doing a runtime error with ZAR chains. Very interesting. So that example does not work right out of the bucket, right out of the gate, which is disappointing. Just make sure I didn't make any typos. Okay, so we need to basically go through and troubleshoot this. I'll be back. Okay, we're back, and I've solved the problem. It was essentially an issue that on where we were getting this compiler error, and it said it needed like freeze support. So I am running this on Python 3.14, and actually in 3.14 for Python, it's not a PyMC issue per se, but for Python, they changed between forking and spawning threads, and so you run into this issue where you need to protect your parallelized code. So all I needed to do here was define a main function and then run that main function in a dunder main environment, and that is inside of this conditional here, and we're good to go. So we can actually run this analysis and see what the result is. Run our linear regression. It sets up all of our stuff. It samples from our probability distribution, sampled 4 chains, 1,000 were for tuning. We'll talk later about what tuning is, and then it took an actual 1,000 draw iterations. But because we have 4 chains, this means it's actually 4,000 plus 4,000 total, and it took 3 seconds. I mean, you can kind of see that with your own eyeballs. So I mentioned before that there were multiple betas, one for each of our for each of our variables. We had beta, beta for sunlight hours, which was going to be 5, and you can see in this example that it reconstructed 4.97, which is not bad considering this is just pseudo-random, right? And also for water, which was originally 20, you can see that it's slightly less. And for soil nitrogen, it was supposed to be 2, and we got like 1.996 out of it. And you can see that these are pretty precise parameters, and there's some various kinds of metrics of how well the sampling actually went. And actually, there's also some information up here in this table too. For example, divergences can be valuable. Step size evaluations can tell us some things. Anyway, so we just built and ran a linear regression. Do watch out for any kind of issues, I would say, when it comes to yeah, just watch out for that concurrency thing. So Python 3.14, you may find that this example doesn't actually work right out of the box, and that you have to either put it in a main function, or you could change your version of Python. I think there might also be some more advanced things you can do if you want to have more control over the threading, but we're going to keep it simple here. All right, so they gave us this summary, and actually it should be, because we have the same seed number and similar versions of the software, look at that, it's pretty much, it's very, very similar, not identical. So there must be some differences in versions of the software, differences in the pseudo-random sampling, but it's very similar. So we can do more than that. Let's go back to our linear regression, and we'll leave that print statement. And let's look at simulating new data conditioned on inferred parameters. So this part, like this sampling, remember that's the posterior distribution. That's the probability distribution over your parameters. Now we want to actually sample new data from that same model, using what we've learned from the sample to generate new samples. So we're going to call this new data, PM draw, PM normal dot dist shape. We'll do a 3x3 there, and we'll say random seed is equal to our seed number. Okay, and we'll also create new chords, new coordinates. So new chords, and we will take, look at this fancy dictionary operation here. We'll take the original chords, and then this pipe operator is actually just going to union the two dictionaries. So what we're doing is we are overriding part of it and keeping the rest. So here we have 0, 1, and 2 for our new coordinates. Great. So now let's build our new model. Well, actually, sorry, correction. It's the same model. Some things you can do with PyMC actually are adjusting to create a new model, but here we're just sampling more data with our inference model. So here we're going to take PM and we're going to set data. And here we're going to pass in a dictionary of our new x data, close that dictionary. In coordinates, we're basically overriding the old coordinates with new coordinates. Look at that. And then we'll give the instruction to sample. So here we're going to sample posterior predictive. Notice that this is neither of the things that we've looked at before, right? Like up here, we were sampling from the prior predictive, but this is the posterior predictive. And that is yet again different from sampling from the posterior here, which is just called sample. This is the posterior predictive. So it's like the prior predictive, but it's been informed by the data that we've, in scare quotes, have fit it to the model, fit the model to the data. My goodness, words. Okay, so we need to pass in some things. One is we'll pass in our inference data, predictions equals true. Does it give us a description of what that actually is? Predictions. Flag used to set the location of predictive samples within return data object. I see. Whether it's going to include them. Obviously, we're making predictions of a kind, so I just wanted to double check what that meant. We're going to do a random seed because we want to be able to run this over and over again and get the same answer, just computational reproducibility. And then we will say PM stats. We'll get a summary with our, we should assign this, they're doing that, new predictions. So the predictions parameter with the true argument means that the predictions are going to be in the new predictions data structure, which of course we want. And we're going to say PM stats summary, put in our new predictions, and the kind, we're going to call it a statistical summary, a stat summary. And let's also print that. So it's going to do a bunch of work. One thing that's inefficient about what we're doing, where you could use a notebook, I suppose, is we're just rerunning a bunch of stuff. Okay, so we got another error here with our main function, I see. What kind of error? Set PyTensor explicit verbosity to medium or high for more information. Vectorized input. Let's take a look. Did I put in a typo here. Inference model. Oh, did I read from this? Let's make sure that I got this right here. We defined our new coordinates. 0, 1, 2. Yep. Inference model. Set our data. X new data, new chords. Great. Oh, they don't assign this to new predictions. My mistake. Aha. Oh, we're adding this into the inference data. Sometimes I make this mistake, and I'll try to make it a little bit less of jumping my eyes too far down where I was reading this, but I actually want to read and go through this. So let's fix that. We have our sample posterior predictive, we have our inference data, we have predictions true. We want to extend inference data true. Also still pass in our random seed. And here, instead of new predictions, which won't exist yet, we're going to go inference data and grab predictions. And I think I still want to print that. Because I assume that they expect that you're putting this into a notebook environment or something, so it won't print. Could be wrong, but we'll find out. So it did some sampling. Yes, it still has a problem here. Set PyTensor config accept verbosity. For more information, I can. But the issue here is vectorized input has an incompatible shape, 0 axis. I think I have a typo, which is one of the downsides of doing this. You know, typing it all out basically live in front of you is I'm going to make these kind of mistakes, and one of them is really just a issue here of yes, okay, that's the distribution. That seems to be right. Let's go back to the top of this. Generative model. Just to make sure that I haven't put in some kind of bug up to that point. Let's run our example. Run. Sample from the distribution. Beautiful. So that's not where the bug occurs. I kind of doubt that this is where the bug occurs. There must be like a typo. I'm just waiting for it to go like, oh, I couldn't see that. Okay. That's also good. Let's look at that. This is quite an inefficient way to debug, but I wanted to keep this simple, and I mean, dare I say, with the problems I've had so far, is it really painless? Is it really user-friendly? Maybe more than what it otherwise would be, but I think that this already highlights some difficulties with making changes. There's a subtlety to the syntax that I must be missing here. So with inference model, because there's now a warning here, you are resizing a variable with dimension trail, which is initialized as a mutable dimension by another variable x. Remember to update that variable with the correct shape to avoid shape issues. Set data, variable name. Yeah, that's not what they're doing here, is it? And yet, in point of fact, I think letter for letter, this is the code. This is the right code. PM, set data, open a dictionary. Key value is x. New data. Coordinates. This is chords and trial, 0, 1, 2. Distribution shape, looks good. There might actually be Z, we got a bug. This could be an issue with, you know, versions. Maybe it is actually properly tested up to a certain version of these packages, and that I'm missing something. So I think it's probably time to debug this. So I'll spare you going through that because I'm just going to do lots of Googling and reading. I will be right back. Okay, we're back, and the problem has been more or less solved. So the first and, of course, most embarrassing issue is just a little typo of somewhere up here, forget exactly where, but I had like trail instead of trial. Clearly we want trial for this example. So that was the more obvious of the two things. But the other thing is that the documentation here really does tell us to use this PM stats summary, iData predictions kind stats. And I found that by removing the dot predictions and instead putting in this group equals predictions, that seems to have solved the issue. I have a gut feeling that this has maybe something to do with RViz changing. Could be wrong, but alias for stats module RViz. Yeah, I don't want to dig into that right now, but suffice it to say, I think that RViz is going through some API changes, and this could be one of the issues where the example doesn't quite line up. So it may depend on the particular versions, and if I was being more diligent, well, they don't actually tell us exactly what versions they use. So there you go. Watch out for that. What versions am I using if I go import RViz? Ooh, that's a hefty package. 1.2. Okay, so those are the things that you have to solve to get rid of that error, and now we can finally look at what we're getting out of this. We'll run the whole process again from the beginning. And so now we get all the same steps we did before of here's our sampling from the posterior distribution, and then getting some summary statistics. It's still getting our 5, 20, and 2 more or less, and then getting samples from our posterior predictive distribution, and here's just a statistical summary of the growth for 3 different plants. Estimated estimates including 14, 24, and minus 6.7. So this last one, on average, had negative growth. But there's a lot of uncertainty in each of these like a half standard deviation or whatever. And then, of course, some of these other statistics, which we'll cover at some point. Okay, so that's already quite a bit. I don't want to labor on the statistical details of what those tables are, but suffice it to say, we've gotten to the point where we're creating synthetic data for the purpose of making a simulation. We are making our model learn from samples of data, and then we are also making new predictions based on the updated model. So that's actually pretty cool. The last thing we're going to do is create a kind of scenario. So we're going to simulate new data under a scenario. Let's do it. We'll go simulate new data under a scenario where the first beta is 0. This is the kind of thing that you can modify in a pretty straightforward way even after fitting the model with PyMC. Is you can do these kinds of model transformations, I think is what I like to call them, but depending on whether you're thinking about do calculus explicitly, these are sometimes called graph mutations, mutilations, whatever. Strange terminology in that space, but okay, we're going to use this do operator thing. Replace model variables with intervention variables. We're basically making replacements to the components in the model. And we'll pass in some stuff. Our inference model betas. And that will be that looks like the same thing. Am I reading that right? Inference model betas, inference model betas, multiplied by, I'm not sure if this is some kind of operator overloading, what this means exactly. But we're going to do it. So this is basically an adjustment in terms of the parameters. Is 0. There we go. Whereas before, they certainly were not 0. Okay, and then we're gonna give this a name, plant growth model. Who knows why that name? You could pick a different name. New predictions. And here we're gonna sample posterior predictive, but this is kind of a posterior predictive under a synthetic scenario that we've created. Predictions true, random seed is equal to seed. Great, assigned to seed. And then we'll do another summary, PM stats, summary, new predictions, kind, stats. And we'll see if we need to do some debugging or not, but we'll run this last code example. Fingers crossed it works. Here we go. We're sampling from the posterior, and we got an error. What's going on here? The inference model, typo. All of that sampling from the posterior predictive, and we are back into error territory. I think that we probably need to do something similar to before, where we go group equals predictions. Let's try that out. Great. So then we got our output table, and this is dealing with a different kind of counterfactual scenario, and so naturally we get some different results out of that. Anyway, that's our first kind of look at building some PyMC models, some of the things you can do. I think some of the things that really make PyMC distinct is a combination of the flexibility of the interface to build whatever model you want, combined with the kind of workflow steps that you may want to add more data in pieces, and then also that you can create new models from models you've already made. So that's pretty great. And then, there's the citation, which I won't read, but basically, yes, there is this paper from a little while ago. Maybe at some point we'll go through it, but not today. And then, of course, there's a BibTeX, so you can add this to your documents, and there's a digital online index number, and sponsors and past sponsors, and I think that's great. So that's probably more than enough information for this first video. We're going to continue on to the next section, which I will see you in shortly.